implicit differentiation. So far, we know how to find the derivative of the functions given by the form of y equals f of x, right? For example, y equals 3x squared, and y equals, you can take the derivative, right, which is 6x. And you have y equal e to the 2x, right? And you can also do the differentiation, right, which is e to the 2x. We use the chain rule, right? The derivative of inside the function 2x would be 2 times e to the 2x, right? Okay, we can do the derivative if you are given y equals a function of x, okay, which is called the explicit form. Okay, this is called explicit form. So that means you can write y in terms of x. However, for some cases, for example, it's not easy to write down the y as an expression of x. It's not easy, right? For example, for this one, it's not easy to find the solution y equals something. But we still want to compute dy over dx, right? We still want to do that because this one tells us the slope of the tangent line of this curve, right? Of this curve. This represents a curve in the space. So we still want to calculate the derivative of y about x. So this is the slope of the tangent line. So if we know the point, then we can calculate the slope of the tangent at that point. Then we can find the tangent line to this curve at a certain point. So how do we do that? So for this kind of function, then we can say that y is an implicit function of x. Okay, so that means there is no explicit form for y in terms of x. However, we know y must be certain function of x. Okay, so here, for example, for here, right, for the different x, you will have the different y value. So y is a certain function of x, but we just don't know the explicit formula, right? So we say y is an implicit function of x. So here, for the implicit function, there is a very important thing you should memorize, you should keep in mind, what is y must be, you must treat y as a function of x. Okay, y as a function of x. So for example, let's look at a very easy example. X times y equals 1. Of course, let's do the method 1 to find the derivative of y about x. Of course, since this is too simple, we can calculate, right? We can calculate y in terms of x. Y equals 1 over x, so dy over dx, take the derivative, would be, this is the 1 over x is x to the negative 1, so it's negative times x to the negative 2, right? We use the power rule. But if we want to treat y as an implicit function of x, in other words, we don't want to calculate, we don't want to express y in terms of x explicitly. How do we do that? But keep in mind, y should be a function of x. So now let's take the derivative about x on both sides for this equation. Let's take the derivative about x on both sides. This is the 1, right? So the right side, the derivative about x for the function 1, constant function, which would be 0, right? The left side is x times y. Remember, y is a function of x, so which is a product of two functions. One is x, the other one is a function of x, which is denoted by y. So we have to use what? The product rule. Okay, the product rule, which is the derivative of the first function, right, times the second function plus the first function times the derivative of the second function. All right. So this one is 1, right? So 1 times y equals 1 plus x dy d over dx equals 0. So we want to know what is dy over dx, right? So we solve for dy over dx. So it would be, we subtract y divided by x. So this would be negative y over x. Okay, so some students may complain why you have the different answers. One is negative x to the negative 2. One is negative y over x. Why you have the different answer? You should have the same answer, right? So here the one thing, for the implicit differentiation, it's very common you have y and x on one side in your solution. However, for this simple problem, okay, since you can write y in terms of x, so actually you can see these two answers are exactly the same. These two answers are exactly the same because if you plug in y equals 1 over x, right? This we know y equals 1 over x from this equation. We know y equals 1 over, if you plug in y equals 1 over x, so it would be negative 1 over x divided by x, so which is negative 1 over x squared. So you see, these two are exactly the same. These two are exactly the same. Okay. So this is the typical way to take the implicit differentiation. So now let's look at more examples. So we want to find the dy over dx for the equation y cubed minus 5y minus x squared equals negative 4. Okay. So what we should do? We take the first step, we take the derivative about x for both sides. So we take the derivative about x for the right side, left side. Then for the right side. Then we take the derivative for each term. Minus dy and the derivative about for the 5y minus d of dx, take the derivative for the x squared. So the right side is the constant, take the derivative would be 0, right? So now let's look at each term by term. Let's look at the first, the derivative. It's the y cubed, right? But we take the derivative about x. So remember, y is a function of x. So this is just exactly, you can treat this y cube as a certain function of x raised to the power third. So, which is a composite function, right? The power third function composed with y of x. So the outside function is the power 3, right? So we can use the chain rule for this derivative. So the outside is the power 3, so it would be the 3. The inside function is y, so keep y to the 3 minus 1, so it's 3y squared. So multiply by the derivative of inside function. Inside function is y, so y over dx. Okay, so you cannot treat this one as 0 because this is y is a function of x, so this derivative exists. It's not 0. So minus, we can take the constant out. dy over dx, it will just dy over dx. Minus, take the derivative for the x squared about x. So this would be just 2x equals 0. So now, we want to find the dy over dx. So here is dy over dx. Here is another dy over dx. Let's combine these two terms. So it's 3y squared minus 5 times dy over dx minus 2x equals 0. So dy over dx is equal to 2x over 3y squared minus 5. So this would be your answer. So it's very common, right? You can see we have x, y on one side. Okay, so this is the one example. So this example tells you the typical way to find the implicit differentiation for function y about x. So keep in mind, you should always treat y as a function of x. Then you have this term, okay? You need to use the chain rule. So now let's look at another example. X squared plus y squared equals 1. So first, we still want to find the dy over dx, okay? Equals 9, sorry. So we want to find the derivative about x. So we'll take the derivative about x for both sides. So the right side is 0, no problem. The left side is the derivative about 2x squared plus the derivative about for the y squared. So the first derivative is just the 2x, right? Because this is the x squared, we'll take the derivative about x, which would be 2x. Plus this term y squared, which is the composite function again. This is the square function composed with the y of x. Okay, so we can use the power rule. We bring down 2, right, and subtract 1, so you have power 1. So then plug in, subtract 1, right, so you have power 1. So then you plug in the inside function is y of x, so which is y. Then multiply by dy over dx. So this is actually some application. The implicit differentiation is an application of the chain rules, right? So let's rewrite. This is 2x. This is the 2y times dy over dx. So remember, we are looking for dy over dx. So you treat dy over dx as an unknown. So this one would be negative x over y, right? So now let's continue this one. The second part is we want to find, we still continue this example. We want to find the points where this curve has a horizontal tangent line. Horizontal tangent line, so that means, so this tells you the derivative, right? Which is the slope of the tangent line at anywhere on the curve. So here we want to find the positions or the points where this curve has a horizontal tangent line. So we need to know what is the slope of the horizontal tangent line. The slope of the horizontal tangent line is 0, right? The slope is given by this formula. So it must satisfy the dy over dx is 0. dy over dx equals negative x over y equals 0. So what does this mean? This means x is equal to 0. Right? Y cannot be 0. Y is in the denominator. So if a fraction equals 0, so the numerator must be 0. So x equals 0. So we need to find the points, right? This is just x coordinate. So what is the y coordinate for this point? Okay, so here is when x equals 0, we plug in the original equation for this curve. What is y? So you plug in x equals 0, so you have 0 squared plus y squared equals 9. So y squared equals 9, y equals what? Plus or minus 3. So you have two values. So in other words, when x equals 0, y equals plus or minus 3. So you have 2 points. One point is 0, 3. Another point is 0, negative 3. At these 2 points, you will have a horizontal tangent line. So now let's look at why this will be true remark for this problem. Because we know x squared plus y squared equals 9, which is 9 is 3 squared. So this is a circle with radius 3, right? With radius 3, negative 3. So here is 3, here is negative 3. So you can see the horizontal tangent line is here. These lines tangent the curve at these 2 points. This point is 0, 3. This point is 0, negative 3. Right? So you see our answer is correct. So now let's continue this example again. Continue this example.